Welcome to Lecture 2 on the topic of Graphical Positioning Systems, or GPS. My name is Dr. Nikki Cooley, and this lecture is part of the subject Future Farming Technologies. This subject is part of the Bachelor of Agriculture and Technology offered at both North Melbourne Institute of Technology and Melbourne Polytechnic. Please visit our website www.nmit.edu.au for further information about this course and other courses that we offer. In Lecture 2 we are going to cover the student learning objective number 2, that is to examine and evaluate different technologies such as graphical positioning systems information, and we will in later lectures look at sensing. So let us start with a simple introduction to graphical positioning systems. This is a technology which is often abbreviated to the letters GPS, and I will be using this abbreviation throughout this course. It is a technology that uses hardware and software tools to collate a number of observations, measurements and descriptions. This information can be used to explain observations and for forecasting. The technology is used in a wide range of applications. From an agricultural perspective, these include a spatial information handling system. They can be used to improve overall decision making on your farm. And they also enable data to be remembered and raw data to be processed in a way that can enable that decision making. In recent years, they have enabled some tractor units to become completely automated. Commercial GPS units come in all shapes and sizes. This is a picture of the units that we use in this subject. You can get more sophisticated units that cost hundreds of thousands of dollars, and you can also get modified units now in smartphones. Some of the capabilities of these units you can utilize through Google Earth and Google Mapping. The purpose of a GPS system is quite simple. It is to calculate and display the location of the unit on the Earth's surface, i.e., it can tell you where you are. This allows the location of the Earth to be determined and recorded. It also is used as a navigation tool. Many people will own one of these and use them regularly in their vehicles. GPS units comprise of a number of components. These components are referred to as segments. There are 3 segments in any one GPS unit: the space segment, the control segment, and the user segment. So let us learn about how this technology works by exploring each of these segments. Let us start with the space segment. As its name suggests, it allows the GPS unit position to be determined. Data is collected from satellites in order to determine the location. These satellites are collectively termed the Global Navigation Satellite Systems, and there are several that are available. It depends on which country you are in at the time of data collection as to which system you will use. In Australia we use the Navstar GPS system. There is other systems such as the GLONASS, which is the Russian Space Force system, and the Galileo system, which is used extensively in the European Union areas. The Navstar uses 6 orbital planes and 32 satellites to enable location determination. The image on the screen will help you to understand how the system works. Each satellite rotates around the Earth's surface in an orbit. The orbits are shown on this image by lines. You will see that there are a number of satellites that orbit or rotate around the Earth at any one time. It is these satellites where the information is transferred into your GPS hand unit. It is the information from the satellite signals which enable your hand unit to determine where you are. The satellite signals send out 2 pieces of information. The first is the location of the satellite when the information was requested or sent, and the second is the time the code was sent at. Satellite signals are transmitted as codes. There are 2 codes that are transmitted from each satellite. The first code is the Course or Acquisition Code, or CA for short. This is also called the SPS, Standard Positioning Service. The second code that is sent out is a P code. However, note that this is a restricted code for military use only. The codes are carried out on L1 and L2 frequencies. In these satellite signals, they contain 2 forms of data: Emphorus data and almanac data. So let us look at the Emphorus data. It is data that contains orbital information which is used to accurately calculate the location of the GPS satellite. This data is highly detailed. It is valid for no more than 4 hours, and a complete copy of this data is required for a position calculation. The almanac data contains information about the position of other satellites in orbit. So let us review. There are 3 types of data required in order for a GPS to work. We have now looked at the space data. In summary, space data is communicated via satellite signals. From each satellite, there are 2 types of data: Emphorus data and almanac data. This data includes location and time of the GPS of the satellite, and codes that tell location and time and whereabouts of other satellites. To complete the space data, you need data from at least 3 satellites. This is why the almanac data is important in the information processing, as well as the Emphorus data that gives the obviously needed codes for location and time. The second segment is the control segment, and this maintains correct satellite orbit. The components of this segment are 1 central station, 16 monitoring stations, and 4 ground antennae. All of these are needed to communicate the information correctly. The user segment is the last segment to examine. This is the unit that collects the data, and it can be stationary or moving. The 2 images on the screen show you examples of GPS user segments. The one on the left is an expensive Trimble GPS unit, and the one on the right is a unit that is attached to a tractor, which enables location and records to be stored. So, how does it all work? Well, the satellites of the GPS broadcast specifically coded signals which is assembly to any GPS unit. Each satellite signal contains the code of its location. Using a minimum of 4 satellite locations, the GPS unit computes its current location. This is displayed by 3 units: AX, AY and AZ, and is referred to as the waypoints. Just to make this clear, a waypoint composes of an X, Y and Z coordinate. The method of computation is done using simultaneous equations based on the 4 positions of the satellites. There is a lot of maths in this technology. Therefore, each satellite encodes its location with an X, Y and Z waypoint. Each one is assigned a number. On the screen you can see the waypoints from 4 satellites that are positioned around the GPS receiver. The satellite on the left-hand side, for example, gives an X waypoint, a Y waypoint and a Z waypoint, and they are each assigned X1, Y1 and Z1. And so this relationship continues until the data from 4 satellites or more are collected. Upon receiving data from the 4th satellite, this is used to synchronize the satellite and maintain the accuracy of the equation. The more known satellite positions and the strong signals generally increase the accuracy of the computation. Therefore, the more satellites, the more accurate the output is. When you are determining a location, you will often use coordinates. In the GPS terminology, These are called waypoints. The waypoints come from the geographic discipline, and they represent latitude, longitude and height. The projected x, y and z coordinates are based on a mathematical formula. In order to interpret the waypoint data, grids are assembled. The grids used in Australia are the Australian map grids, and they are suspended by the map grid of Australia. Different countries will use different grid systems. With respect to datums, these are currently in Australia the Geocentric Datum of Australia, GDA 94. You need to make a note of these when you are using GPS units, as it's important that you map the correct grid and the correct datum. Otherwise, interpretation of your waypoints may not be correct. Now that you understand some of the inputs to get the GPS data, you will understand how this may drive accuracy. The GPS unit requires at least 4 satellites within direct line of sight. If it does not have this minimal requirement, then it cannot calculate accurately the location. The interference, such as a tree canopy, building, or topography, will affect accuracy considerably. Recording from a moving vehicle may result in errors up to 500 meters, although this area of technology is advancing at such an astonishing rate, thanks to the use of satellite technologies in motor vehicle industries, that this error, particularly around cities, is less and less. In order to minimize errors, good satellite coverage is important. You require a minimum of 4 satellites, strong signals, and a good satellite position. Errors can be measured in DOP, or dilution of precision units. The image below shows you 2 different dilution of precision measurements. The one on the left hand side gives a unit that is low, 1 to 5, whereas the one on the right hand side gives you dilution of precision measurements that are high, 5 to 7. The most simple GPS device you can get is a handheld GPS, a TwoNav. In concept, instructions are quite simple. You turn the machine on, you select a walking function, use menus to check satellite availability, which includes the position, the strength and the number of satellites available at that point in time. You create waypoint files for the data. You mark your waypoints using your menus and label appropriately. Save this data into your saved file, and turn off after use, as the battery consumption is quite high and battery lives tend not to be that long. The image on the slide illustrates some of the common errors that can occur to a GPS signal. These include orbit error and clock error. Both of these errors occur on the satellite. The next 2 errors are errors that occur due to delays between the signal being sent from the satellite to the GPS unit. An ionospheric delay occurs in the ionosphere, while a tropospheric delay, as its name suggests, occurs in the troposphere. The final error that this image described is a multi-path error. These can include such errors as signal masking. Some of these errors and other concepts will lead to sources of signal degradation. This is called a selective availability. This means selective availability of the data. Some of these errors include multipath errors, the receiver, the troposphere and ionosphere, the nearly perfect clocks, and obstructions to the satellite signal. Occasionally, the US Department of Defense will randomly offset the timing of CA signals. This is to maintain security. This ensures low accuracies, and these could not be achieved by civilian use. Multipath errors are errors that occur when signals reflect off surfaces. Multiple signals from one satellite can be received, and this is also results in a multipath error. Long delay signals are recognized easily when they occur. Antenna can be designed to mitigate some of the short and multipath errors that may occur. Receiver errors are those that can be measured as a signal-to-noise ratio. Errors that occur when the signal is being travelled through the troposphere and the ionosphere occur as the signal varies in travel speed, which is caused by two different densities of both of these atmospheric layers. Minimal errors occur directly overhead, while greater errors are nearer the horizon. Errors can be partially rectified by modelling once the GPS unit's approximate position is known. Emphasis is where data of the satellite location must be timely and accurate as possible. When you're using GPS infrastructure, you want clocks that give you as nearly accurate timing as possible. Atomic clocks are regarded as more accurate than quartz. However, these clocks are large and heavier, and this makes their practical receiver usage compromised. There can be obstacles to the satellite signal. These include physical obstacles which disrupt the line of sight. Some examples of physical obstacles you need to be aware of are topography, buildings, machinery, and severe weather. There are methods to improve accuracies. These are in the form of correction. Corrections can be made by comparing the results from known locations or making calculations based on other parts of the satellite code. These are what we refer to as differential GPS and RTK. Differential GNSS attempts to correct timing errors given by a CA signal. It uses the code phase of the satellite and a second receiver to find a correction factor. It then applies this correction factor to the other GNSS readings. The illustration shows some of the concepts behind differential GPS. To increase accuracy, differential GNSS can occur through a network. That is, there is a number of known stations which act as a network. This increases the number of observations and therefore increases the accuracy of the rover unit. RTK, or real-time kinemeric, this is a facility that increases the accuracy of the position of roving units by providing corrections from a reference receiver via a communication link. Errors are calculated using the carrier phase of the signal, and this in turn increases the accuracy of the position. Continually operating reference stations act as part of the RTK network, and they can provide continued uninterrupted differential GNSS satellite information, thus resulting in greater accuracy. RTK positioning services will provide data to customers. The image on the slide shows you a networking process center and how data may flow. You can see a number of reference stations are communicating their data to a central data processing network. This central data processing network is then able to send or communicate that information out to the rover station. GPNet is a positioning and navigation correction service for the Global Navigation Satellite Systems, GNSS, which operate throughout Victoria, Australia. It provides a networked in real time of kinetic data corrections. The following map gives you some idea of the complexity of the connections required. You can see how they cover the entire area of the state of Victoria. This technology aids significantly increasing accuracies of many GPS units. In the GPS network, there are over 100 reference stations, which are called CORS, or Continuous Operating Reference Stations. Network Differential GNSS provides sub-meter accuracy statewide. This facility has been a significant improvement in the accuracy and the ability for this technology to be used effectively in agriculture. The following table presents a comparison of positioning methods that are currently commercially available. They critique accuracy, range limit, correction method, and how they are used in agriculture. Please spend some time studying this table. If there is any component of this lecture that you have not understood, you may wish to visit the following resources, and they may help you with your understanding. Please note, these resources are not essential, but only information to support what you have learned here. In this lecture, you will hopefully be able to now detail what GPS technology is. You should be able to describe how the GPS technology works, understand how the technology can be compromised, and describe how GPS accuracy may be enhanced with a suite of additional tools and technologies. This brings us to the end of Lecture 2 on GPS.